a spring, right? Do you see a spring? Or maybe it's better to do it like this. I'm not sure which way it's easier to see spring. Okay, so we'll assume it's I guess for now we'll assume it's horizontal. It might be vertical, but horizontal is kind of easier to set up. And at the end of it, we have a mass. I'm here or there. I'm not sure which picture you want to refer to, as long as you understand what I'm talking about, a spring. And now that spring with that mass is oscillating, moving to the right, moving to the left, and going back and forward. And we want to describe the movement of that object at the end of that spring. Okay? Does it make sense? Set up equation, set up an equation. To describe the movement system. So let's see how we're going to set up. So we're going to start working with forces. So our general equation, force equals to mass times acceleration. So mass times dv dt, right? Because we're talking about the spring. So spring, if you recall the Hooke's law, do you remember that? Negative kx. So Hooke's law says if we will have extend or press the spring, then the force which is exerted by the spring is proportional to the displacement from its equilibrium position. So what we'll assume that somewhere here it has equilibrium position. Yes, V equilibrium position. Then we measure how much displacement we've got from that equilibrium position. And Hooke's law says that the force by the spring is proportional to displacement from their equilibrium position, and it's in the opposite direction, right? If you extend it, then try to go toward the equilibrium position. So Hooke's law says it equals to negative k. So far, so good. Okay. Then also we might have friction force. And as we did before with air resistance, we will assume that friction force is proportional to velocity and in the opposite direction. So we'll assume that friction force is, I cannot use K anymore, so I guess I will use B. B times V, and negative because it's in the opposite direction. Are they good so far? And possibly some over external force. For example, you have a hand which is pushing that object or doing something else. Possibly some over external force. F external. Okay. Now let's put all that information together. So we have mass times acceleration, that's a force, equals to force by that spring minus ky friction's force minus BV, and maybe external force F. Now you recall how velocity, position, and acceleration connected, right? So if y is displacement, then acceleration is second derivative of displacement, velocity is the first derivative of displacement, and I guess F external is F external for external force is external force. So recall that y acceleration is second derivative, velocity is the first derivative, right? So we're going to get our equation. Mass times second derivative equals negative ky minus b times first derivative plus F external. And if you like, move everything on one side. Plus ky plus by prime equals to F external. And here we assume k and b are greater or equal to 0. That's our differential equation, which is going to model the situation. And that's exactly what we're doing so far. Assume so that's second order differential equations are not homogeneous. So if F external equals to 0, then we're going to get homogeneous. So let's do that example. I guess before I do that, I will use some notation. That coefficient k in front of y, right? So it comes from Hooke's law. So it tells us how steep that spring is, right? The bigger k, the steeper that spring is. Okay. So it's stiffness. Okay. But friction force, which we have here, we also will often it's going to be equivalent to the damping force. Damping force. G at okay. And we'll refer to B as a damping coefficient. So B is the damping coefficient. So the bigger the B, the bigger the damping force is. Okay. So now let's see what kind of picture we're going to get if we assume that example. If we assume that there is no external force, and we assume that there is no friction. Then you can easily see what's going to happen, right? So if we start the spring and there is no friction, then it's going to be going to the right, to the left, 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 right? So that's what we expect to see. It starts somewhere and will be oscillating between that equilibrium position. Depends on initial acceleration, depends on where initial position is. So our system is going to look like my prime plus ky equals to 0. And we expect the solution to look like, so I assume time here, I assume y here, and I will expect it to be oscillating up and down, right? Does it make sense? From physics point of view, again, it makes sense because if there is no friction, then it will go up to the right and to the left along their equilibrium position. Okay. So, but that's exactly what we. So that is what we could confirm by doing calculations. Because just imagine we're doing calculations, we switch to corresponding auxiliary equations, mr squared plus k equals to 0. So mr squared equals to negative k, where k is greater or equal than 0. So r squared equals to negative k over m. So r equals plus or minus square root of km times I. So we have our solution, y equals sine of square root of k over m t, I guess, plus cosine of square root of k over m t, c1 here, c2 there. That's exactly what our solution suggests. So we're going to see either cosine or sine function, or maybe combination of both. You also can interpret a little bit more about, say, about the frequency, and say how k and m will affect the frequency, how fast it will be rotating. I mean, not rotating, oscillating, or how slow it will be oscillating. So that's first. Now let's move on a little bit further. Next example. Well, we'll assume we have external force equals to 0. Still right with that. So m second derivative plus b first plus ky equals to 0. So let's not do it. Keep writing. Then we will have two possible situations here. Okay. So we might have that friction relatively small. So damping force. We might have it small. Okay. So if it's small, then what will be happening with that spring? So it will oscillate, but the amplitude of oscillation is going to be smaller and smaller because we still have a friction. So it will still oscillate, but friction will slow it down. Okay. So what will be happening in this case? So y and t. So it starts moving, but that oscillation going smaller and smaller. That makes sense? So if that's happening, we're going to call it under damping. Quite often we want to avoid friction, and we want to have that coefficient of damping coefficient to be as small as possible, right? So that's under damping. So we want to move in without friction. The opposite picture we can get is then the damping force is big. large. Then what will be happening here is basically it starts moving and basically it slows down almost immediately as soon as it gets through that equilibrium position. So it cannot go very far. Right? So what I mean, picture might look something like this. So it will not be oscillating. So here it will start moving and then it will basically doesn't. Okay. It will not pass anymore through that equilibrium. So that is overdamping. Okay. If it makes sense. And let's do problem 2. Say mass equals to 1, B equals to 2, and K equals to, say, 2. Okay. So we have our equation, second derivative plus 2, first derivative plus 2y equals to 0. That's a model which describes that mass oscillator. And the question is it over or is it under damping? What kind of picture we're going to see? Is it going to be oscillating? Is it going to be oscillating back and forth? Maybe slow down eventually, or it will be slow down almost immediately. So overdamping is, we want to observe overdamping, for example, when we are riding in a car, right? We don't want our car bounce up and down, up and down, up and down. So we want it bounce and then not bounce anymore. So overdamping is useful when we're talking, for example, about where shock system in a car. So that's where we want to have big friction, so everything will be slowed down relatively quick. So overdamping. And underdamping is when we want to have to avoid friction, right? So for example, when we're talking about clock, right? Especially those old clocks, they keep moving for a long time. So okay, anyhow, so what kind of system is that? If we switch to corresponding auxiliary equation, so we're going to get r squared plus 2r plus 2 equals to 0. I haven't done that for a while, but let me complete square. R plus 1 squared plus 1 equals to 0. R plus 1 squared equals to -1. So r plus 1 taking square root of both sides equals to I. Square root of -1 is I. So r equals -1 plus I. So our solution here, e to the negative t cosine t plus e to the negative t sine t, and put your coefficient C1 and C2 here. That's a solution. And just looking at this solution, you immediately see, for example, the first one, it's basically your cosine function. And that coefficient e to the negative t in front, what it will make it eventually disappear. So when time going toward infinity, e to the negative infinity will go towards 0. So the same with the second coefficient. So when time approaching infinity, that will be equal to 0. So we're going to have displacement is going to be 0. That's what we expect to see because we have damping coefficient. We want it to slow down. And you see also it's not going to slow down immediately because we have cosine and sine functions. So it will be going up and down, up and down, up and down. So that is under damping. So we have under. So let me try. I kind of want to get minus number, but I'm not allowed to use number. So believe that will work. So let's see the general solution here. We're going to solve auxiliary equations R1 equals negative 2 and R2 equals negative 1, right? 2t plus e to the negative t, right? C1 and C2. And you see we don't have any sine and cosine, and that is not going to oscillate because we have only exponential function, and all that the exponential function will do will go either up or down, and that's it. Maybe they will cancel each other once. That's why you're going to get that one little bump, right? So, but there is no sine and cosine functions, and sine and cosine functions, that's what will do it going up and down and oscillate. So that's over damping. So that's how solution will also tell you about under damping and over damping. So under damping, we're going to have sine and cosine in our final answer, right? The general solution. Over damping, we have only exponential.